I hope you remember this from Cal 2. When you were trying to find the Taylor or Maclaurin series, that you had to do a formula that looked like this. All right, that's n. It's summation. And you tried to come up with that formula. Yep. And so what you did is you took successive derivatives over and over and tried to find a pattern. Well, I'm just saying that because in calculus we have had to take like derivatives repeatedly. So here I'm just taking some derivatives, partial derivatives over and over, but I'm changing it up. So what about this first one? We're going to do partial of f with respect to x first, right? And that, we're doing this first. We're moving from left to right. So what is that partial with respect to x? 2x minus 30x squared y squared. Now partial with respect to y. So that would be negative 60x squared y. Now partial with respect to y again. Negative 60x squared. And then finally partial with respect to x, right? Which is negative 120x. Okay, y'all get this. We won't do part B. All right, this is just a very, very quick little, in no way, shape, or form can you say, we did Laplace we did Laplace in Cal 3 today. No, I'm just very quickly introducing you to what a Laplace equation is. So in mechanics, heat dynamics, fluid flow, electrical potential problems, this equation comes up. And what you're trying to do in these applications is you're trying to find functions that satisfy this equation. A solution to this equation, right? A solution to this equation would be something you do in like differential equations, trying to find a function that solves this equation that involves partial derivatives. Now, I'm going to use a different notation than what's used up here. Oh, I do it. Never mind. It's right here. This is the same thing as this. So if somebody gives you a function of two variables, I'm using u instead of f. Someone gives you a function of two variables, and you do the partial of this with respect to x twice, and then you add that to the partial with this with respect to y twice, and if you get 0, then that function is a solution to the Laplace equation. Any function that satisfies that is called a solution to the Laplace equation. So in the next thing, what I'm going to do is I'm going to give you a function and ask you whether or not it's a solution to the Laplace equation. So is this a solution to the Laplace equation or not? What do we need? We need uxx, we need uyy, right? So what's ux? Partial of u with respect to x. 3x squared plus 3y squared. Okay, uxx. 6x, and that's it, right? All right, we need to find out what uyy is. So uy, partial of u with respect to y. 6xy, right? What's uyy? 6x. Okay, is this a solution? No, the Laplace equation says this. uxx plus uyy has to be 0, right? So not that these are the same, but these actually have to be opposite in sign for that equation to be true. So is this a solution? No, it is not. It turns out that all the solutions to the Laplace equation all kind of look like something. They all have some property that makes them unique. Sign, yeah, we need something in there, right? What's that? Yeah, yes, it would involve some trig. Trig functions, sine and cosine. All right, implicit differentiation. So I'm going to try and see if you remember this. So before we do this, okay, act like you're back in Cal 1. And I ask you to find y prime, which is the same as dy dx.
Is that y squared?
That's y squared. Yeah, sorry, I kind of... So back in Cal 1, if we had this right here and we were asked to find y prime or dy dx, we could not solve for y. You cannot isolate y right now. There's no way to get it by itself. So what we did was we did implicit differentiation. That means we took the derivative of both sides of the equation with respect to x, because this says with respect to x here. So when we did the derivative on the left side, we would, anytime we took the derivative of x, we did the regular old derivative, but then we treated y like y prime, right? We said y prime, like derivative of y would be y prime. All right, we had to do product rule, chain rule. We had to keep that all in account. We want to do the same thing here. All right, we want to look at an equation like this. Here, notice that this is not solved for z. Do you see that? And it might be difficult for us to get z by itself. So, because there's three variables here, I cannot ask you for dz dx because this is a straight up derivative. And I can only do partial derivatives when I have more than two variables in my equation. So I can't do this. So this is the notation I'm going to do. So anytime I take the derivative of, like over here, when I took the derivative of y, we said y prime, right? Anytime I'm over here and I take the derivative of z, I'm going to say kind of like z prime. But I'm going to use partial notation instead. And then when I take the derivative of x, I'm going to just do normal derivatives, right? But how am I going to treat y? Like a constant. See, we didn't have that over here. We never treated any of these variables like constants, did we? We treated x like, okay, derivative of x squared is 2x. But when we got to y, we said y prime. Here, when we get to z, we say z prime. When we get to x, we say regular old derivative. When we get to y, we say, y is being held constant. Let's do it. I'm not going to do this one. You do this when you have an equation that you cannot isolate z. All right, what is the derivative of x cubed with respect to x? How do I know it's with respect to x? Because the bottom says it's with respect to x. So derivative of x cubed is 3x squared plus what's the derivative of y cubed? 0, right? Because I'm holding y constant because this is a partial derivative with respect to x. Plus derivative of z cubed. Be careful here. 3, close, 3z squared, then dz dx, but I'm going to use partial z with respect to x. You have to remember you've got to do the chain rule, right? You've got to do the chain rule. You've got to take the derivative of z cubed, the 3 pops out, it becomes z squared. Then you take the derivative of the base, the z, which is partial of z with respect to x. Is that all right? Pardon? Yeah, and that's what we're solving for. So it needs to pop out somewhere, right? And then keep moving. Oh, uh-oh. Oh, uh-oh. Y is a constant, though, and it's attached to functions. Yeah, let me write it this way. Kind of look at it this way. Y is a constant. It's going to come out with the 6. Ignore this. What's the derivative of x times z? What are you going to use here? Product rule. Right? You've got to use a product rule there. So watch how I write this. Plus, I'm going to put 6y, and then I'm going to do my product rule here. You don't have to do it this way. You can do it all together, but I like kind of pulling the constant out, doing my product rule right here. Derivative of this product is derivative of this, which is 1 times, so z plus, now derivative of z, partial z with respect to x times x. And then we'll distribute the 6y through.
So I'm a little lost as to why on the first z cube we have the product.
We did power rule. Power rule, not product rule.
That's how we got 3.
That's it.
Squared.
Uh-huh.
Where is that?
This? Chain rule. Look, okay, because let's do it this way. Back in Cal 1, if I asked you to take derivative of this, right, you would say 7 comes out. It would be this to the 6th. But then you would say times the derivative of what's inside, right? Yes? Times 2x? 7x squared plus 1 to the 6th times 2x. That would be the derivative of this. Yes?
Yeah, for power rule, but
No, for power rule. And this is power rule and chain rule. When you look at z cubed, you have to understand that you're doing the exact same thing. The z is like this stuff in here. And so when you take derivative, 3 comes out, z squared, that's this. But then times the derivative of what's inside. What's the derivative of z? dz dx. Why didn't we do it here? Okay, well you did do it though. 3x, right? 3 comes out, x squared, times what's the derivative of x?
1.
With respect to x, it's 1. So there really is a 1 out here. We just never write it. That make a little more sense? It's because the reason why you don't write it here is because it turns out to be dx dx, which is 1. The reason we have to write it here is because it's the derivative of z with respect to x, which is not 1.
so if it was derivative of z with respect to z,
Then it would be 1. Yep. Okay, good question. All right, I'm not done, right? What else do I have here? Finished off. I finished this off, right?
Yeah.
Okay, equals what? 0. Derivative of the other side is 0. So now you have an equation. Let me clean it up a little bit. It's 3x squared plus 3z squared partial z with respect to x plus 6yz plus 6xyz partial z with respect to x equals 0. So I just kind of rearranged some stuff here, distributed through, and I'm trying to solve for partial z with respect to x. So everything that doesn't have it, move it to the other side. Anything that, any term, these terms right here, I'm going to leave on the left side. I'm going to move everything else to the right side. 3z squared partial z. Why am I doing this? What am I about to do?
Factor out the
Question, did I mess something up?
Yeah, you shouldn't have a z there.
Where's that?
Right there.
Oh yeah, I don't know why I put the z here. This 6y goes to here, x. Thank you. I was getting a little ambitious there. Next one, 6xy partial z. So I was saying, why am I doing this?
So you can factor out.
So I can factor out the partial on the left side. So when I move these over, these both get turned to negative, right? And then factor out the partial and then divide through, right? When I factor this partial out of these, it comes out, put parentheses, and then divide through by all that stuff. So I'm going to just write the answer now. It should be negative 3x squared minus 6yz over 3z squared plus 6xy. There it is. You'll have to, yeah, that'll be in class for sure. You'll have to do something like that, yeah. What is the difference between part A and part B?
One's the y, that's the x.
It's with respect to y.
So x is
So x is a constant. So when I start taking derivative of this is going to be what? 0. 3y squared. 3z squared partial z with respect to y, and then so on and so forth. Okay. Something subtle here. I'm going to give you a comparison. Y equals x squared versus sine xy equals x plus y, and then versus that one up there. These are all equations, right? These are all equations. This one contains just two variables, x and y. If I asked you for y prime, you'd say 2x, right? And in order to find the slope of that line, all I have to give you is x, right? I give you x, you're going to tell me the slope of the line. Here, I don't know if you recall this from Cal 1, but for implicit equations like this, when you get down to y prime, most of the time, this is going to have x's and y's in the answer. You're going to have both x's and y's in your answer, which means in order to find the slope of the tangent line, you actually have to give me the ordered pair, the x and the y coordinate, for me to tell you what the slope of the tangent line was. And that's because these implicit equations sometimes drew these really weird shapes. And because you had more than one point corresponding to an x value, you would actually have to give the exact ordered pair. Here, it passed the vertical line test, so you only need the x coordinate. Is that making sense, kind of? Here, look at this answer. We actually have x, y, and z, which means in order to find the partial of z with respect to x, you would have to give me the ordered triple, the x, y, and z coordinate, three-dimensional point of where you are, and then I could supply you with the slope. Does it what?
Because the x, y, z that gives us 3D space.
Well, let's say that you have an equation that involves three variables, okay? Let's do this one. Anybody ever seen that before? Chemistry?
Ideal gas law?
Yeah. So this says that pressure times volume equals number of moles times, I think that's Avogadro's constant. Avogadro's constant, and this is temperature. Okay, so basically these two together right here are constant. Let's just forget those. Those are a constant, all right? This is an equation that relates three variables together, right? If I asked us for the partial of p with respect to t, then we could go through this and do this just like we did this. Here what we would do is we would treat capital T as our variable, right? We would say that when we take capital T as our variable that we're differentiating with respect to, when we got to v, we would treat v like a constant. This is already a constant, right? And what does this represent? I don't know if I'm answering your question. This is what it made me think of. What does this mean? What does this give us? What is this number, this answer, when we plug in it, when I plug something in, when I plug in the pressure, the volume, and the temperature into this answer, whatever I have here, what does it represent? What does that number represent? This is the instantaneous rate of change in pressure with respect to temperature. It's telling you at a specific instant, when the pressure, volume, and temperature are this value, this will give you how fast that pressure was changing with respect to the change in temperature, assuming that your volume is held constant. Understand? Then if you could also do partial P with respect to V. Here, I'm going to hold my temperature constant, and this will give me how fast the pressure was changing with respect to the change in volume. You could even do partial T with respect to, let's go P. You could do that. This would tell you how fast the temperature is changing with respect to a change in pressure. Now, if you've ever had a soda can, right, and you've ever had like a soda at room temperature, and you open it up, right, it's like, whoosh. I don't know if you've ever noticed, but that gas, when it's released, is always a little colder than it was inside the can. Like that air is going to be colder, and it's this right here. What happens is, think about this. If this equation has to be true, then if you decrease temperature, right, if this number gets smaller and this has to maintain its equality, what has to happen? This side has to get smaller too. And the only way this side can get smaller is if the temperature drops. That's why when you release something, that change in pressure, drop in temperature, that's the way air conditioners work, right? We compress Freon, compress it, and then spit it out this little orifice. And when it comes out the other side, it's under less pressure. It releases the pressure, and the temperature has to drop. And then it goes back through and continues to go through that cycle. Recompress it, spray it out, drop in temperature. Freon's just really good at that, at doing that. When you change the pressure, Freon has a huge drop in temperature. All right. Again, I digress.
So with what we were, X, Y, and Z,
Yeah.
whichever one will hold the constant, basically going to tell us which direction we're really looking on the surface. Because it's giving us the rate of change between the Z and X, but one of them's held constant, so that would give us that plane almost.
Yes, but I just want to make sure that when you say that, let's say that we hold y constant, okay? If we hold y constant, then that's basically we're pointed in a direction. See, how do you describe that direction to me, though? If we hold y constant, I'm basically standing on a curve, pointed in a direction, and all I can tell you is that that direction is what? Like parallel to the xz plane. I'm okay with that if you want to look at it that way.
Yeah, so basically it gives us our direction that the tangent is facing.
Yeah, exactly, yes.
And the change of Z or the change in X is going to tell us that instantaneous rate of change.
That up and down. Yep, it's telling us that up and down. As I move x, how am I changing? All right. There's the homework for that. I'll bring this up at the end of class. I have 15 minutes. I still want to talk. Tangent planes. Just remind me, I'll put that homework assignment back up at the end. The reason why I want to do this is because this is super, super fast. There's not a whole lot here. It's just one quick formula. We don't have to prove this. I'm just here to provide it for you, all right? Tangent planes to a surface. Now we bring this all together and you get a formula. If you have a function of two variables, which should be a surface, and that function has continuous partial derivatives. That means you can take the derivatives, the partial derivatives, and those partial derivatives are well defined. They don't have any crazy things happening to them. Then the equation of the plane, which is tangent to that surface, at the point x naught, y naught, z naught, is given by this. Now that might look crazy to you, but I'm just to point something out. Do you remember the general equation of a plane? It looked like this. A, x minus x naught plus b, y minus y naught plus c, z minus z naught equals 0. That's the general equation of a plane. Do you all see that in here? Yes? Here's your z minus z naught, y minus y naught, x minus x naught. That means this right here is A, right? And that means this right here is B. And that means that C is always -1. Wasn't that the direction vector? A, B, C was the direction, the normal vector. I said direction vector. Normal vector of the plane?
Yeah.
So that's why I say that right here. The normal vector of the tangent plane. I think in my notes that I had printed online, I didn't put vector. I just put, so the normal of the tangent plane, which is fine, but I decided to put vector in there. So the normal vector of the plane is this. These give you the coefficients. And this is good. This is good because if I'm trying to find the tangent on a surface at a point, then all I need is the point in the normal vector. The point I'm going to know because you're going to tell me where you want me to go look. And the normal vector is just a computation. I have to take a partial with respect to x, plug in my point, take a partial with respect to y, plug in the point, and I'm done. We good? Sorry. Okay. All the notes are online. Yeah. All right, so this is the one I was going to do in class, but I think I'm going to decide to do a different one because I want to do one that we can visualize like before we even start the problem. All right? So scrap that for now. Let's look at this right here. I want to see if we can predict what our answer is going to be before we even do the work. There's your function of two variables. And I want us to find the equation of tangent plane at 0, 0. I'm picking something that we should be able to just think through and get the equation just by thinking. Okay, that's going to be a dome, top half of a sphere. What's the radius of that sphere? 1. So the picture of this is this, right? And I'm looking at the point 0, 0, which should be the origin, like this, right? And that should go straight up to that point that's at the top of the dome. And then my tangent plane should just be a flat plane sitting on the top of that dome, right? What is the equation of the plane that's just sitting on top of that dome? Z equals 1. Because z equals 0 is the xy plane. Z equals 1 is the plane that's moved up 1, right? Yeah? Sure? Okay. I wonder if we can get that same result. That's just us thinking through it, but let's try and follow this method. All right, so according to the formula, I need to know what is the partial derivative with respect to x at 0, 0. I need to know what is the partial derivative with respect to y at 0, 0. Let's see if we can do those. I'm trying to get the normal vector of this plane. Right? You know what I'm saying? I'm trying to get this and this piece right here. So I need some partials. So let's take our partials first. Oh yeah, I'm going to need chain rule. So that's what I'm going to need. Let me go ahead and do my partial with respect to x first. So what is the derivative of the square root of anything? 1 over 2 square roots of that stuff, right? Times the chain rule. The derivative of what's in here with respect to x. So I'm treating y like a constant. So 0, negative 2x, 0. So negative 2x. And what does that become? Negative x over root 1 minus x squared minus y squared. Yep, that's what f, partial of f with respect to x is. Everyone agree with this? Now that since we've got it up here, let's just figure out what is the partial with respect to x when you plug in 0, 0. Well, you're going to plug in 0 for x and 0 for y. So 0 up here, we get 0. Let's just make sure we don't get division by 0 here. We're okay?
That's 1.
That's 1, so we get 0 here. So that means that normal vector that we're looking for, the first component is 0. What's the second component? Take the partial with respect to y. Are we going to get the exact same thing as this with one slight change? It's going to be negative y instead of negative x. If you work through it again, the only difference is when you take derivative of what's in here, you get negative 2y. Things cancel. So this is going to be negative y over square root of 1 minus x squared minus y squared. Now plug in 0, 0. And you should get 0 again, right? What else? Are we done? Do we need any more work here? We need the point, though, don't we? Don't we need the actual point? We need x naught, y naught, and z naught. I know what x naught, y naught are, right? That was 0, 0. But we never actually figured out what z naught was. So we have to plug 0, 0 into the original function to figure out what the z coordinate is on that sphere. And if you plug in 0, 0 here, you get 1. So this right here is 0, 0, 1. We're almost done. I'm ready for the formula. The formula is going to be, it's on the previous note, it's the partial of f with respect to x at the point 0, 0, which was 0. Then x minus x naught, which was 0, plus partial of f with respect to y at 0, 0, which was 0. And then y minus y naught, which was 0. This is very boring. Okay, plus, but no, the formula says what? Negative 1 always, and then z minus 1, because z naught was 1, and that must equal 0. And then when you distribute this through, you get negative z plus 1 equals 0, and if you move the z to the other side, you get z is equal to 1. Now this is definitely the harder way to find the tangent plane, because you could have just maybe thought through it, but I wanted to show you that if we think through this, we can get this answer. Let's see if the formula actually produces the same thing, and it does. That's in no way a proof that this formula works, but it helps us feel a little bit more confident that it works, right? See this. We have 5 minutes. Oh, let's do the sign-in sheet. When was the last time I did that? I remember. Does anyone need the take-home exam? Yes? All right. After, get it from me afterward. Let's see, 9:27. Okay. No, this is yours. Those are yours. So if we're trying to find the equation of the tangent plane here for this one now, you can kind of look at it like you need three things, right? You need x naught, y naught, z naught, so you need a point, right? And then you need the two components of that normal vector, and those you get from the partials. So do y'all want me to do this, or y'all feel comfortable with it? You feel all right? Okay. We have 5 minutes, but everyone's got to sign in, so I'll work it. I'm not going to say a word, though. I'm just going to sit here and work it. Once you sign in, you're free to go.
I just got a little update on my phone as we were leaving that gravitational wave detection, like the fourth sign of gravitational waves.
What?
The wave detector for gravitational waves
Uh-huh.
got a notification that they detected a fourth one, fourth signal. So they're getting closer and closer, proving like they're one or two.
For what? The quark thing, or what?
No, the gravitational wave detector, the first two that they found, they like concluded so far that it was two black holes that merged, and then the third one that they found, they thinking that it's two neutron stars that merged, and then this fourth one just happened. God knows what that is.
Is price of gas going up or anything? No.
It's just really cool.
No, I know. I'm just giving you a hard time. I'm just giving you a hard time.
Even if price of gas did go up, there's no gas prices.
What do we got here? -2. I think that's it. I went through that real quick.
And then to find your z coordinate, you would just put in those original coordinates.
Well, in this one, they actually gave us the whole thing. So
But that's the equation of the plane.
that's the equation of the plane that's tangent to that surface at that point. So this piece right here is that number. This piece right here is that number. This is always -1. Then this is your ordered triple written in here, and then
I have a question for you that's not part of this class.
okay. We'll talk about that in a second. Let's. Oh yeah, I'll put the homework up, and also there's a homework for this one, because that's the only example I do. Oh no, I do another one. Darn it! But let me give them both to you. Okay, so that's problems 1 through 6 on page 648. And then the other one is that one. Everybody have a good weekend. When's that take home due? Wednesday next week, huh?